Okay, our next speaker is Nik Kinkel. Nik, if you could come up. Okay, Nik is an undergraduate student at Iowa State, majoring in software engineering and mathematics. He's also a research assistant at Ames Laboratory, a DOE Office of Science lab, located in Ames, Iowa, and affiliated with Iowa State. Nik has been working on flow-based analysis for the past year and a half, focusing on aggregation and semantic analytics.
Hi everyone, so my name is Nik, and yeah, I'm from Ames Laboratory in Ames, Iowa, and I work pretty closely with cybersecurity analysts at Ames Labs. So this talk is going to focus primarily on some implementations we've made at Ames Labs, some of the challenges that have come up as we're looking at analyzing flows and specifically augmenting them with semantic information, and some of the progress we've made over the past year. We presented last year at FloCon, so this is going to focus on some of the stuff that's come up over the past year. So first off, let's give a quick overview of what semantic augmentation is, what are some of the problems we're trying to address, and what does the domain look like. So when we look at flows, we have all of this statistical information. We have packets, bytes, records, and we can get a lot of information from this, but it's very hard to get context or meaning for these flows from just stuff like duration or the last time we saw this flow. And what we really want to worry about is this resource important to us? Is it related to the mission of our laboratory and what our network and organization is trying to work with? And specifically for us, we're looking at this in the context of addressing cyber attacks and possible threat alerts that are coming in. We want to be able to say, is this resource important? Do we need to worry about it or not? Can we just take some kind of auto response, whether that's block or just ignore this attack, whatever. So that's kind of the core problem that we're looking at. And we want to be able to try to categorize or classify these different kinds of flows and IP addresses and hosts that are talking to us. So we want to be able to say, is this resource primarily related to something like shopping or entertainment, in which case, for us at our organization, we probably don't care. And if we get an alert from some kind of address that's, we think is associated with shopping, we can probably just go ahead and auto block. On the other hand, if that's a resource that's associated with education or with another government lab or a military site, that's probably something that we care about. We may be storing important information on that network. We may have researchers doing collaboration. That's something that a human needs to know about and we need to do something about. So we're looking at how can we figure out how to put these flows in context and add meaning to them. So I'm going to give a quick overview of what our system at Ames Laboratory looks like, kind of how it works in day-to-day operations and how we've implemented things. So at the top there, we do a process, we say once per period, and in our case, that usually means once every 24 hours. So what we're really trying to do is assign some score to a bunch of IP addresses, and by looking at that score, that should tell us how related to our mission is that host. So our score that we found the best results with is by looking at the lexical similarity from some input text. And so what we do is if we have lexical data, and that can be collected generally from scraping other people's websites or from collecting a bunch of their textual information. So if we have data, we can then compute the cosine similarity from that set of data to some input text. So maybe from a mission statement for our lab or from our own homepage. It actually doesn't matter as long as it's some significant text that represents our organization. So we compute the cosine similarity and get some score, and that score goes in a database. Now, if we don't have any textual information, which is the case for a lot of addresses, so it may be some dynamic IP out there, or someone that doesn't have a homepage, or it just might be something that we don't have any information for, then we just have to try to make a good guess. So we have a classifier that currently is using a support vector machine that tries to say, if we had lexical information, this is what the score would probably be. So we aggregate all of that in a database, and we do this once every 24 hours. Now, in the real-time part of our system, we constantly have alerts coming in, and these can be from intrusion detection systems, it can be from cyber threat sharing frameworks, wherever. We just constantly have alerts coming in, and we want to use our client, talk to that database, get the score, and we check a threshold. And now if this score is below a threshold, we say it's probably not related to our mission, we probably don't care about it, it's okay to take an auto response, and that auto response in our case is just blocking. if it is important enough, that's something that a human being needs to look at, and we send it to an analyst and they can look further. And interestingly, a big challenge that we've found is actually how do you choose what that threshold is? How do you say, we can assign everything scores, but where's the cutoff for what's important and what's not? And we've tried a bunch of different approaches. We first started off saying, let's say every analyst can look at, say, 10 serious threats a day and investigate them and dive into them and see, what's the context and meaning of this threat. So that tends to kind of work, but then we also, say we get 15 very important threats a day, then we're just ignoring maybe 5 very important resources. So what we've kind of settled on is an iterative process with our analysts at the lab, who they will just sort of start off arbitrarily choosing a threshold, and they'll see, do we get important enough stuff here, and do we not lose enough stuff here? And then we'll kind of work with them, slide that threshold up or down until we find something that works well for us. So now I'm going to talk about augmenting this data semantically using this lexical information, and specifically some of the challenges that we found in collecting this data and actually being able to use it, especially at scale. Even with a small to kind of moderately sized lab like Ames Lab, we've had scaling problems. So we have all of these different semantic data sources, like service type, is it SSH, SMTP, whatever. We can look at host names, so is it a .edu or .gov? If so, for our organization, we probably care about that a lot more. We can look at time series information, do some graph analysis, which I'll talk about later, or we can compute this lexical similarity, and that's probably, as we found, that's the most meaningful, but in some ways it's also the most expensive. So we're looking at ways that we can make this cheaper and easier to actually use. So we see that there are a bunch of challenges in getting lexical data. It's expensive to be scraping all the time. That can get our machines blacklisted or get angry emails from system administrators, and we can't have that at the lab. We can't just be scraping constantly. And it also makes for a very complicated installation process for our software. So we can't just say, oh, here's some nice software, but we need about 2 weeks of flow data, and then you have to scrape for a week constantly before you can use it. That's really not good enough. So what we settled on is finding a large public data set, so we don't have to do any scraping ourselves, and parallelizing our solution, I guess, on Amazon Web Services using Hadoop. And that gets us much better performance. We don't actually have to do any scraping anymore, and we can outsource all of this work and only do it, say, maybe once a month, because organization homepages are not changing that often. So to look at the actual process of how we do this, and again, the point of doing this is we want to figure out, for as many resources as we can get, we want to find out what is the lexical similarity from this resource to us, to our mission statement, to our homepage, whatever. And it's not just for some organization's homepage. We usually take their homepage, choose 20 random links off that page, and get data for all of those pages. So we feed in some kind of seed statement, like a mission statement, and we'll go through. So we're using a data set called Common Crawl. Common Crawl is about 200 terabytes of data. It's just a big public web crawl. There's about 2.8 billion web pages there. So that's our input data set, and they've made it very, very easy to use Hadoop on Amazon Web Services. So we initially, for every host name we compute the cosine similarity, and since we're using multiple different web pages, maybe 20 or so, we'll get a bunch of different results. So by the time those results get to the reducers, we take the maximum score, and that's what we save. And there's a couple nice advantages of doing it this way. So one is we can run multiple batches at the same time. So recently, we ran about 6 labs at once. It's very nice, and we only need to do this, once a month or so. We're still figuring out exactly how much this is going to cost doing it over the long term. But our last run, it took about 3 days, but we chose the absolutely cheapest instances possible, and it cost about $65. So if you look at the overall cost in terms of political cost of having to run scrapers all the time and possibly getting angry emails or machines blacklisted versus just the time, it's much, much faster than actually having to go out and grab a bunch of textual data. this is much cheaper, and also it tremendously simplifies our install process. So instead of actually having to ask people to go out and get that lexical data themselves, we just say, if you want, give us some input data, and we'll give you back a giant list of the lexical similarities to your resources, or they can just run this themselves, and that way we don't have to even be involved at all. So it's much, much simpler. I kind of talked about Common Crawl already, but one thing I'm going to highlight is coverage. So one of the big questions we had is, for the resources we care about, that we look at, how many of those actually wind up in this public data set for Common Crawl? And so for all of the IP addresses that we saw in a 2-week period at Ames Lab, we were able to get good, valid host names for about 13 or 14% of those. A lot of those are dynamic addresses that just randomly allocated. So we were able to get good host names for about 13 or 14%, and we do our lexical data collection on host names. So of those 13 or 14% of host names, about 7% of those wound up in Common Crawl, and that's approximately as good as we get actually doing real web scraping. So we're pretty comfortable with that, and that's more than enough information that we need to feed to our classifier to get good results for stuff that we can't actually compute the similarity to. So now I'm going to talk about some semantic augmentation using graph analysis. So this is an approach that is still very much in development for us. We're actually, my partners back at the lab are running experiments actually as we speak. And this is something we hope that can, in the future, possibly replace some of the lexical analysis as a way that's maybe cheaper and faster. So what we want to do is look at the characteristics of relationships between external hosts that talk to resources on our network, and based on the characteristics of those interactions, figure out how they're related to each other, and see if we can extract some meaning out of that. So if we look at the set of all the external resources who talk to our internal resources, we can immediately observe that that graph is kind of naturally bipartite, right? So in the following slides, the white nodes are going to be external resources that talk to us. The red nodes are going to be internal resources on our network. So first off, and this is building a bit on what we did last year at FloCon. So last year we said, let's just cluster everything and let's try to build a complete graph and see how that works for us. So first off, just doing this naively is very, very, very expensive. And in fact, the bipartite graph is approximately complete. And so one, it's very expensive. Two, we don't get much meaningful information from it. So we need to find, and the way that we actually build this graph is we just draw an edge. If there's any traffic whatsoever, then we draw an edge. So it turns out that this is not very useful, partly because it's so expensive, partly because we just don't get much information from it. So we have to make some optimizations. So the first optimization that we can do is filter the edges somehow. And the way that we've settled on is only draw an edge if we see some kind of interaction over time. So let's say maybe let's say a 2-week period, we'll only draw an edge if these two resources interact at least once every 24 hours in that 2-week period. And that immediately makes the graph now usable. It's no longer complete, it's much smaller, and we get much more meaningful semantic information out of that graph, because now it's highlighting those interactions that happen on an ongoing basis and are therefore much more important. So the other large optimization we can make is, instead of looking at every single external resource, we can group them by autonomous system. And this grouping by autonomous system lowers the cost in computation time from on the order of hours to on the order of minutes. So it's much faster, much more efficient if we do those two optimizations. So what we want to do is do a bipartite projection and look at the graph the set of external resources based on their interactions with our internal resources. So as we're drawing those edges between external resources, there's 3 big approaches for a threshold of whether or not those 2 external resources get an edge. And one is called an unconditional threshold. The other is an agent degree condition threshold, and the last one is a dual degree condition threshold. And I'm not going to go into too much detail on those, but the main thing to take away is that they're kind of 3 different levels. So an unconditional conditional threshold is the cheapest computationally, but you lose the most information. Agent degree conditioned is more expensive, and you lose less information, and a dual degree conditioned is the most expensive, but you keep the most information. So we kind of took the middle route. We went with agent degree condition threshold, and so I'm actually going to skip that slide. The final results look like this. This is the graph drawn by doing a bipartite projection on the traffic at Ames Lab over 2 weeks. So if you look in that top cluster, that is core infrastructural resources. That's Microsoft, Red Hat, all that kind of stuff that we talk to all the time. And the size of a node here on this graph is dictated by the degree. The color is actually its PageRank score. So red means a high PageRank score, blue means a low PageRank score. So then if you look in the bottom right corner, that is other universities and other laboratories. So we're looking at, hopefully in the future, being able to actually replace the lexical similarity with this graph analysis. It's much cheaper, it's much more scalable. So now I'm going to talk about some approaches we've had to visualization and kind of working with our analysts to explore this data a bit more and pull out some more meaningful features and things that we can be looking for, both in terms of anomalies and in terms of relationship characteristics that we may not have thought of. So we want to do everything we can to help encourage our analysts to dive into the data and help us figure out what's important and what we should really be looking for. We've had some good results helping with analysts helping us discover relationships that we didn't actually know were important. So we have a tool here, and I'm not going to do a live demonstration because we didn't bring any data, but this is our kind of standard exploration tool. So if you look in the bottom left corner, that is a graph that you can actually change what the axes mean. I think currently there it's a graph of the strength characteristics by the lexical similarity. So as you look at that, the two interesting things to note is that something with a very, very high strength score, but a very low lexical similarity score is something that you may not care about. That's maybe something like Facebook or some news site that people spend a lot of time on, and there's constant interactions, but it's not actually related to our organization through meaning. So if we see alerts for something like that, we probably don't care, and we can probably just take an auto response. Now something that has a very high lexical score and a very low strength score is something that might be really hard to figure out that we care about, but if we get an alert on it, that's something we probably want to know about. That's maybe an upcoming conference or something that is, its mission is very close to what ours is, even if we don't talk to it very much. So this is all released as a free software project. I want to stress that some of our results, we've run this primarily on Ames laboratory data. So this is mainly university data and lab data. So one thing we really are interested in and really want to try is running this on other types of data. So industry data, people that aren't .edu, .gov. That we're very interested in this. So if anyone wants to try it out, just come talk to us. But this is all free software. If anyone wants to try using it, it is a research project, so the installation process might be a little tricky. You may have to come talk to us. So future work, we have some interesting future work that we're still currently working on. So we need to get more statistics on our Common Crawl analysis and see how that lexical information really stacks up to how important these resources really are. And that's kind of a tough question, is really quantifying how do we say how meaningful this is, and how do we know if we've made the right choice, right? Because there's no really, it's very hard to get a true positive and say, oh, this is definitely very, very important. It's really just kind of up to the cyber analysts who say, yes, I agree this is important, or no, it's not. So we're working on quantifying how we say if we're right that this is very, very important. So we're also very interested in looking at applications beyond network security. Currently, that's our main focus, but I think this could be very interesting for other applications. So I want to thank Cloud Helix. They sponsored my student scholarship to this conference. So any questions?
So you mentioned that when you don't have any lexical data that you do SVM clustering. So what are you clustering on when you do that?
Right. Sorry, can you say that question one more time? I didn't catch the first part.
When you don't have any lexical data, you said you do SVM clustering to get a cosines.
Right. Yeah, so let me come back to that slide. So you're talking these slides?
No, it's before that.
Okay. So like here, when we have no lexical data whatsoever?
Right.
Right, so what we do then is we have a classifier that uses currently a support vector machine, and we look at a bunch of different features, and we try to guess and say, okay, if we had lexical data, this is what the score probably would be. Yeah, so we use mainly a bunch of statistical features. So what's the most recent time we talked to them? What's the volume of packets, bytes, records? We look at time series data, and then we use as training data the resources that we do have lexical information for.
All right.
Yep.
Hi, my name's Eric.
Hi.
I'm from Cray. I do graph, so I'm a little happy to see graph.
Oh, cool.
I've got 2 questions for you.
Sure.
Where did you set your thresholds to do your significance?
Right, so that's
relationships?
a really tricky issue, and that's one of the, in terms of actually implementing this, that's been kind of one of the biggest issues for us. So originally, we said, okay, Ames Lab has X cyber analysts. Let's assume that all of them can look at 15 important alerts per day. So let's look back in 2 weeks, see how many alerts we got per day, and we'll set the threshold at a point that says we can say with 99% confidence, you'll never see more than 15 important alerts per day. But then it turns out that may actually hide really important alerts that they should be looking at. So currently, we have this nice little user interface. It's not actually released publicly yet. We're still kind of iterating on it with the analysts, but that they can set a sliding threshold and see if I chose a threshold to be this, I would see these alerts over the past 2 weeks. I would have seen these. It would have blocked these. And so we kind of let them choose themselves, and over a couple weeks, we kind of arrive at a value that they see the ones that they care about, and it doesn't auto-block too many.
So the Nest threshold for your interface, the Nest thermostat, basically you just let them set it for a while?
Yep, they get to kind of tweak it.
Okay, what clustering algorithm did you guys use on the resulting graph once you conditioned the bipartite graph?
So, right, so we, all we really did was just group by autonomous system.
No, so if you keep going.
Yep.
Okay, you did something to that graph.
Right. So we did a bipartite projection from our original graph. Okay. We built an edge based on a threshold of whether or not these two resources talk to each other. Yeah.
Okay, thank you.
Yep, you're welcome.